BH? That doesn't help?
Can we buy a vowel?
Can you buy a vowel?
Yeah.
Well, in the B word, there's only one vowel, and it's an A. And in the H word, there's two vowels, one of them silent, O and E.
What?
What?
Black hole.
Black hole.
Wait, are you serious?
Black hole. All right? A black hole was just a whole lot of mass shoved into a very small amount of space that does gravity super, super, super strong. Right? So strong that the light can't get emitted. Even light that is coming from behind it, right, has a hard time getting around it, let alone through it. So light is responding to gravity. That's weird. Waves shouldn't do that. Gravity is something that gets exerted on things that have mass, right? So a black hole is a very good example that under extreme circumstances, light can act like a particle, right? But most of the time, we don't have extreme circumstances, so it really does act like a wave. All right, so what do I need you to know about diffraction? I need you to know that it's due to the spreading out of wave energy, and that it gives pretty good evidence that light acts like a wave. All right, so now we're going to come back to your color. All right, so our final objective today was to begin being able to predict what happens when we combine colors of light and then colored pigments, right? I would be thrilled if we make it all the way through light today. I don't think we will, but we're definitely not going to make it to pigments today. So the diagram that I have up here is just a very, very, very narrow region of the electromagnetic spectrum, right? It's the region that our eyes can respond to. What part of our eyes actually responds to this stuff? The retina. Right? So we have cells in our retinas that we'll come back to later that if these frequencies of electromagnetic radiation hit them, right, they will send electric signals to our brain, very similar like to how our ears send electric signals to our brain, right? But it's only these frequencies that will make that happen. So we do have names for different chunks of this, this narrow frequency range, right? We have violet over here at the shortest wavelengths, the highest frequencies. We have blue over here. We have green and yellow at the middle frequencies, the middle wavelengths. We have orange, right? And then we have red, which is the longest wavelength of light that we can see, the lowest frequency of light that we can see. And then what's our mnemonic device to kind of remember that order? Well, it used to be, like when you guys were maybe in like kindergarten, it used to be Roy G. Biv. It's not it anymore, right? Now we just do Roy G. Bov. Right? Indigo was removed from that mnemonic device because seriously, nobody knows what the heck indigo is. I don't know what indigo looks like, right? I mean, if you look, here's violet, right? Here's blue. There's kind of nothing in between. So yeah, we don't do indigo anymore, right? No big loss. No big loss. So each of these colors is representing a different chunk of this continuous spectrum of wavelengths and frequencies that our retinas respond to. All right, follow-up questions about that before we do this. What? All right. So, all right, without further ado, the primary colors of lights are, in fact, red and blue and green. And there's very, very straightforward reason for that. Okay? Very straightforward reason. Now, I guess since I said there's a reason, let me give it to you. What is on our retinas? What are our retinas composed of?
Cells.
Sure, cells, in particular photoreceptor cells. So cells that do some chemistry when certain kinds of light hit them. But let's be more specific. Cones and rods, that's right. So let's write some of these things down. So we got the retina, right? And we have rods and cones. Now, anybody, almost can't remember this, but did anybody remember which of these is responsible for color? Hannah? You're right, it is the cones. And the way I am able to remember that is that color starts with C and cones start with C, right? So that's one of the times where it kind of makes sense. So cones can see in color, and rods really can't do color, right? So that's just like light or dark, or like light or no light, yeah. And then how many different types of rod cells do we have? I think it's just like one. How many different types of cone cells do we have? 3. 3. Anybody know what we call them? What, Jesse?
Primary colors?
Well, their name, the primary colors, and the 3 types of cone cells, right, are the same thing. So we have some cones that we call red cones, and some cones that we call blue cones, and some cones that we call green cones. And those, I mean, we're going to look at exactly what wavelengths will activate each of those cones. It's not exactly that the red cones only see red and the blue cones only see blue and the green cones only see green. It's a little more complicated than that. We'll look at the frequency response. But, right, I mean, the blue cones are kind of really good at seeing one part of that spectrum. The green cones are really good at seeing the middle chunk of the spectrum, and then the red cones are really good at seeing the red chunk of the spectrum. Again, there's a little complexity there that I do want to look at, but for right now, I don't. Right, so for right now, I want to just formalize that those are in fact the primary colors of light. I'll try and do 2 different things to show you guys some evidence of that, and then we'll go back into the biology a little bit. Yeah. So again, you have to know for me that the 3 primary colors of light are red, blue, and green. And that if we add those 3 colors together in equal amounts, what do we see? What do we see? If I shine a red flashlight and a blue, I think I can actually do this. I have red here. Now what did I do with my blue and green? I think are in here. So when I shine all 3 of these at Henry's eye, what's he going to see? Pain.
White?
I think he's going to see white. Uh-oh. Uh-oh. Except there might be a missing green. I can't do it. Green is missing. All right. I'll look for my other set of slides while you guys are labbing in a few minutes. All right. So let me cheat. Now, so I said I'm going to do 2 things. I'll try and do 3 if I can find my green slide. I was going to do 2 things to try and convince you that we do in fact see white when we add those 3 colors of light together. The first one is I'm going to show, I don't have 3 projectors, right? You may have seen me expose one of my film projectors. I don't have 3, oops, I might not even have one. I need to do some like yard sale stuff this summer to try and find some more. If I had, oh, there's the green. Forgot that I put it in there. If I had 3 projectors, I would do the video clip that you're about to see by myself, but I don't. So let me cheat, and I'm just going to show you like 2 minutes of, I'm going to show you 2 minutes of one of my favorite physics teachers, and then I'm going to have you try and make it on your own. Now, where did I want? Yeah, I'm having, because my battery died, I'm having this issue with the different views from my computer. 3930 is what I want. We get it ready, and then we'll watch about 2 minutes of this video, and then again I'll try and have you see this on your own while I get ready to blind Henry. So this is going to be a video clip. Where's the little mouse? Of this. So this is a college physics class. It's a physics class at the University of Virginia, right? They're doing pretty good in the tournament right now, I think. And it's actually about how televisions used to work, like not the modern TVs, but the older ones. And so he's just doing 2 minutes on colors. So let me get my, forgot my speakers. Let me get that in. He has 3 projectors, right? The University of Virginia has a little bit more money than Biotech does. So he'll do that. And then you guys are going to do it by using the optics kits, by using the things we use for the test dividers. So that might be kind of exciting to get to see what's inside those. All right, we on? I think so. Okay. Where are you?
This? inside again. Here is source of green light.
Now remember, my projector is awful, but that pretty much looks green, right? On my computer screen, it actually looks greener, but that's pretty green.
Okay? Here's a source of red light.
That's red, for sure.
Here's a source of blue light.
That's pretty blue.
What do you think you'll see if I turn on red and green together?
All right, red and green together. What do you see? Nothing
Blue.
black?
Purple.
Yellow.
Yellow. Yellow. We'll come
So
back to that.
There's no yellow there. It's red and green. The yellow is your eyes responding.
Now again, it's not perfect because my projector's terrible. This really is greener than it looks up here, but I definitely see yellower here than over here. Sorry, it's not perfect.
Those two colors by saying, oh, there must be yellow light. How about if I turn on red and blue?
Red and blue. Who? Orange? Purple? What's that? It actually has a special name. It's called magenta.
You see magenta. And green and blue, you see cyan. I know, they're fancy names. What can I do? And if I turn them all on, you get white.
Alright, that's actually not too bad. Again, the green, my projector doesn't do greens very well, but that's certainly white-ish in the middle. Alright, so I'm going to try and have you do that yourselves using our test divider. So let me get this out to you. Now, we're only doing part 1 on this today. Alright, maybe we'll do part 2 next time. Probably not, because part 2 doesn't actually work that well. So we're only going to do part 1, and then as soon as you have this, come meet me at the desk behind Kara and Victoria.